Hi there. Today we'll see the atmospheric refraction and some of its effects. Okay. So a refraction means that changes the change of the path of the light, right? When it travels from one medium to another. Okay. So this is air and this is water, means it will be going like this, and when it is entering the denser medium, it will bend towards the normal, right? Towards the normal. So only one bending of the light has happened. Okay. But what is what is the case if it is atmosphere? Atmosphere is not a single layer. This is one surface and this is one phase. It is not like that. So atmosphere is made up of so many layers. In so many layers, so there will be a difference in temperature. You know that temperature also affects the density of the medium, right? If the temperature is more means the particles in the atmosphere will be move away from each other, so its density is very less. Okay. When it is cold means the density is more. Okay. When it is hot means your density is very less. Your density is very less means, and the refractive index also will less. Okay. When it is cold means your density will be more. Air density, particles will be very tightly packed, so it is density is more and the refractive index will also be more. Okay. So but if it is, there is only two layers, and that means we can say this is the refractive index. Only the light travels here and it will bend like this, we can say like that. But in case of atmosphere, there are so many layers are there, and the temperature also vary in each layer. Okay. Time to time it is also getting. For example, in the morning in your house we will get a chill air, right? In the afternoon you will get a hot air. Again evening will chill air, right? So likewise, time to time the temperature also varies, and according to the altitude also, distance from the earth surface also, it varies, right? So the light will be reflected in between in many ways, right? So you will not get a straight path of the light, right? So totally we can get a curved path of the light. When it travels through the atmosphere, we'll get a curved. So average of this we will get as a curved light, not a straight line. Okay. So we'll see what is happening in that. Temperature of the air varies throughout the atmosphere. Not only that, the temperature of different parts of the atmosphere changes with time also. Okay. Hence the refractive index of the atmosphere is also varies. Okay. So when light travels through the atmosphere, it travels in a curved path, because so many refraction it has undergone, and we will receive this as a curved path. Okay. Not as a straight line. You know that light travels in a straight path, but here we are consider this as a light travels through the atmosphere in a curved path. Okay. So we can based on all this thing, we can give a definition of this atmospheric refraction. When light ray passes through different layers of air, then refraction of light takes place. This phenomena is called atmospheric refraction. Simply, what is meant by atmospheric refraction? When light passes through different layers of the air, then the refraction of light takes place. Okay. Why there is a refraction of light taking place? Because of the temperature. There will be a rarer medium, denser medium, rarer medium, denser medium. You will get the refraction of light. Okay. Some phenomena based on this refraction are, so because of this atmospheric refraction only, we are having a twinkling of the stars happening. Okay. Stars are present, but why it is twinkling? That is because of the atmospheric refraction. Okay. And the star seems higher than they are actually. Okay. Actually whatever we are seeing that star is, it is slightly higher than its actual position. Okay. Next, advanced sunrise and delayed sunset because of the atmospheric refraction. And planets also do not twinkle because of this atmospheric refraction only. Okay. We'll see in detail one by one. Okay. First one, twinkling of stars. So you know that this star is present here. So you are standing on here. This is take this as earth, and you are standing here. Okay. Okay. So this is your atmosphere. Take this is atmosphere. Okay, this is your atmosphere and this is your earth. Okay, so the light will travel like this, right? Okay, so this would be your center, means your normal would be like this, right? Normal. So since it is travel from rarer to denser medium, it will be rarer, and nearer to the earth surface it is denser. Okay, so it will bend towards the normal. It will bend towards the normal, right? It will bend towards the normal. Okay, so what happens actually, the person, okay, I'll draw here. The person sees from here, actually look at the star at this place. Okay, he'll be seeing, watching this star is appear to present here. Okay, this is appear to present here. Why it is twinkling means, during it has, the light has to pass through several layers of the atmosphere, and here it has to reach his eyes. Okay, so sometime because of this variation, it may be refracted like this. Okay, it may be slightly away from the atmosphere based on the refractive index. So he is not able to see the star. At that time the star will not be visible. Again at some distance he is able to see that, so slightly star will be visible. Again he will get the light rays passing from here, this position. Again it is clearly visible. So it is visible, it is diminished visible and clearly visible like this. That makes the light to his eyes, it flickers, right? So this makes the twinkling of stars. Okay, okay, because this the ray which reaches this person is not constant. Based on the refractive index of each layer, the incoming rays may differ. Okay, the path of the incoming rays may differ. When it is reaching this place, he is able to see slightly. When it is reaches this place, he is not even able to see that. When it reaches this place, he is able to clearly see the light from this star. So it looks like a twinkling of star, flickering to our eyes. Okay, the light will flicker to our eyes, so it happen, the stars are twinkling. Okay, okay. So the light coming from the star undergoes refraction due to varying refractive index at various altitude, right? So one moment the star appears to be very bright, okay, and the next moment it becomes very dim. Okay, this phenomena is known as twinkling of stars, because this variation, right, the variation of the temperature and the refractive index is not constant. It keep on varying. Is the temperature, for example, if the temperature here is 31 degrees Celsius, always it is 31 degrees Celsius? No. At times it may 31 degrees Celsius, becomes 29 degrees Celsius, or it became 25 degrees Celsius, or suddenly it became 35 degrees Celsius. Because of this varying effect, one moment the star appears to be very bright when the light rays reaches our eyes. Okay, the next moment it becomes very dim because it may be away from our sight. Okay, so this phenomena is known as twinkling of star. Okay, and the next phenomena is stars seems higher than they actually are. So same here itself already explained. When the light rays enter the atmosphere, since it is entering from rarer to denser, it will bend towards the normal. So it appears to, the star appears to be present here. So it is slightly higher than the, or shifted from the actual position. This is your actual position. This is your actual position, and this is your apparent position. That is not true actually. Okay, it appears to lie here. Okay, because of the refraction, right? The starlight on entering the Earth's atmosphere undergoes refraction continuously. Since the surface is rarer in higher altitude of the sky and denser nearer to the Earth's surface, the starlight bends towards the normal. Hence, the apparent position of the star is slightly different from its actual position. Slightly move from its actual position. And when this is observed from horizon, the same star is observed from horizon, the star appears slightly higher than its actual position when viewed near the horizon. That means horizon is nothing but the separation between the earth earth and the atmosphere. This is your horizon. Okay, when you observe from here, it is the star would be slightly appear higher than the actual position. Okay, next is your advanced sunrise and delayed sunset. Advanced sunrise and delayed sunset. So that is, so your earth is here and your sunrise means when it crosses, this is your horizon. When it rises, when the sun crosses this horizon, above this horizon, then only we can say this is sunrise. Okay, when it is crosses this horizon and it is below this, we will say it is sunset. Okay, but before it sunrise, we are able to see that. How? Because you are standing here, the sun is here, it is not actually raised. Okay, so what happens? Because of this refraction of light, because of the refraction of light, it bends. Actually, it will come, and since it is enters this, it bends towards the normal. And he is able to see this. Okay, actually he is able to see this, and it looks like sun has raised. Okay, I will draw again. This is the horizon. The light rays will be bent actually, but to him it is not bent, it is raised. Okay, clear? Now it is clear? Okay, fine. See, if you draw a normal to this point, it will bend towards the normal, not away from the normal. Okay, this is what happening here. So before its sun rays, we are able to see that. Okay, likewise here in the sunset also. Even if it's sunset, we are able to see the sun here. Okay, that is called advanced sunrise and delayed sunset. Okay, the sun is visible to us about 2 minutes before the actual sunrise and about 2 minutes after the actual sunset because of the atmospheric refraction. Clear? Okay, the actual sunrise means what? I mentioned the actual crossing of the horizon by the sun. Whenever it crosses the horizon, that means your sunrise. Whenever it crosses down the horizon, it is sunset. Okay, so what will be the difference between the actual sunset and apparent sunset? The time difference between actual sunset and the apparent sunset would be 2 minutes, about 2 minutes. It is not exactly 2 minutes, it's about 2 minutes. Okay, and one more thing also happening because of the atmospheric refraction. Atmospheric refraction phenomenon is responsible for apparent flattening of the sun's disk at the sunrise and sunset. Okay, why they mentioned during the sunrise and sunset means because sunrise and sunset happens when it is crossing the horizon. Okay, when it is nearer to the horizon, there will be the light rays bend slightly more. Okay, can see the flattening of the sun disk effect only near the horizon, because only near the horizon the light rays bend slightly more. Means, see, flattening of the disk means this is your earth, this is your earth. Okay, this is your horizon. When you are in the horizon, okay, when you are in the horizon during the sun rays or sunset, what happens? For example, this is your sun. Okay, the light will be bent and it will reaches your eye, right? Reaches your eye, but actually the light rays will not bend, right? So for you it appears to be like this. Okay, that's why it gets flattened. Clear on this? Okay, flattening of the sun disk also due to the atmospheric refraction. Clear on this? In the place of sunset and the sunrise. Okay, its last phenomena is planets do not twinkle. Okay, so why it does not twinkle means the planets are much closer to the earth, right? And thus seen as a extended source. It is not a point source. From the star you will get a point source of light. Okay, you will get a beam of light. Okay, if it is when it reaches your eyes means it will look bright. When it does not reaches your eye means it will be dim. So that's why you will get the twinkling effect of the star. Okay, but this is an extended source and it is very much close to the earth, right? So we are going to consider this as a planet as a collection of large number of point sized source of light. Okay, so what happens, for example, think that this is a planet. Okay, this is going to be the collection of large, I'm going to start mark this as a, this star is this planet is made up of a large number of stars. That means you can take this all the stars as a point source, single point source. Okay, you take this as, okay, what happens when you are here, when you are observing from here? Okay, what happens? Due to the refraction of light, some of the stars will, what happen, some of the stars will rays will reach your eyes, or some other may not reach your eyes, right? It may be like that or it may be like that. Only few things will happen. Okay, when this light from the star is dim, this may be bright, this may be bright, this may be bright, this may be dim, this may be bright, this may be dim, this may be bright. Okay, so the total effect variation will be very less. Okay, even the shifting, the whole shifting, since it is very big, the shifting of the apparent position is not, we are not able to notice that apparent position of the planet. Actually it will also, due to the refraction, it will also be visible in this place, but we are not able to notice that the apparent position of the planet. Okay, we can able to see only its actual position. Okay, since it is too large in size. Okay, only few things will be dim at a time and more lights will be reaching his eyes. Okay, so the variation is very less and it becomes when it compared to the so many number of individual stars, when compared to the one or two, that one or two it will be get nullified. If you take the average, it will be 0. Okay, so that makes that planets does not twinkle. It will be always glowing like that. Okay, so it can be taken as a collection of large number of point size source of light. Therefore the variation in the amount of light entering our eyes, variation in the amount of light entering our eyes from all the individual point size source will be average out to be 0. Okay, therefore thereby reduces the twinkling effect of the each other. So the planets do not twinkle. You know that if it is a star, if it look, one single beam of light will come, when it reaches you it will be bright. When it does not reaches you, it will be dim. At that time it will not be visible, it will be dim. When again it reaches you, it will be bright. Bright dim, bright dim, bright dim will give you a twinkling effect. Okay, but this planet is made up of so many numbers of individual stars. Okay, if one star is dim means, will this affect this whole light? No, from all other stars you will able to receive the light rays, so there will not be any twinkling effect. That's why planets do not twinkle, due to the atmospheric refraction. Clear on this? So we have seen the 4 phenomena based on the atmospheric refraction. What are the? Twinkling of stars, stars seems to higher than they actually are. Advanced sunrise and delayed sunset, planets do not twinkle. Okay, thank you.